which is the following. Assume that we have an identity which is written as this: 5x squared minus 6xy plus 5y squared. This is equal to 0. So what we see here, we have an expression which is it is a nonlinear expression. It is nonlinear because we have x and y which are to the power 2. In linear algebra, we want all the variables to be to the power 1. That is why we consider it to be linear algebra. Now, one possible question can be here. Why are we discussing here some nonlinear expression? How can we make this one more adaptable to the linear algebra? To this possible question, we can answer like this. We can try to represent identities like these by describing this polynomial as this is equal to 2, by describing this polynomial as a vector x transpose times the matrix A times the x again. Now, then we can ask the following. How can we do this? How can we find an x, matrix A, and another x, to reformulate these terms, which, if we have here x squared and y squared, probably we can hide these square terms in the multiplication of x and x transpose. Now, one possible way to do this is the following. Let's assume that this x transpose, we can write this one as xy, okay? What is the size of this vector? This is 1 by 2. Let's multiply this one with 5, minus 3, and 5. And this is the matrix, which is 2 by 2. And we multiply this one with x and y. And the dimension of x and y, it is 2 by 1. And this is equal to 2. Okay? So if you multiply all of these components carefully, you might notice that as a result, you are going to get a scalar quantity, or you are going to obtain a matrix which is 1 by 1. Now, okay. If you multiply all of these terms, this is what you are going to get. And now, let's assume for a moment that we have a Cartesian coordinate system. And,
Professor,
yes.
Sorry to interrupt. I have a question.
Yes.
How did you choose the numbers in the middle matrix? 5, minus 3, and 5.
I choose them because I want this answer to give me this. So, Lou, help me here. What happens if we multiply this matrix with this vector?
You get 5x minus 3y.
And then?
And minus 3x plus 5y.
What is the dimension of this vector?
2 by 1.
2 by 1. If we multiply this with x and y, what is the dimension of x and y?
1 by 2.
1 by 2. So if we multiply these two, what do we get?
You get a single entry. So you get
5x squared, right? Minus 3x. And then? Minus
3x squared.
Plus 5y squared, right? This is equal to 2. Would you agree?
Yes.
Okay, so this is what we get. So then, can I erase this one? No?
Yes, it's clear now. Thank you.
So, yeah, sure, it was a good question. We should be able to see that. But now, imagine for a moment that we have a Cartesian coordinate system that looks like this. Now, this Cartesian coordinate system, this is the standard basis, and we have here 1 and 1. Now, let's try to rotate this Cartesian coordinate system, and let's bring this like this. Rotate it by an angle of 45 degrees. Here and here. So, let's assume that this new coordinate system, this is capital X, and this is capital Y. Now, if this is capital X and Y, this is our previous X and Y. And let this angle be pi over 4. Okay? And again, we use the language that we have. What is the standard basis? It's 1, 0, right? And 0, 1. And now we are going to get a new basis. So, but for now, let's just say that here we have x, y, and here we have the capital X and the capital Y, okay? And then we want to rotate the variables, but and the rotation matrix is, what is the rotation matrix if the angle is pi over 4? The rotation matrix is going to be cosine pi over 4 times minus sine pi over 4, okay? Then we have sine pi over 4, and here we have cosine pi over 4. What are these numbers equal to? We have 1 over square root of 2 times 1 minus 1, 1 minus 1, 1, 1. Okay? And then, who can help me with a relationship between the new coordinate system, which is capital X, capital Y, with the little x and y? How are they two related together? So let's assume the rotation is this matrix A. So let me denote this as a matrix A. Then what equation can we write? So would you agree that we can write the following? X and y is equal to the matrix A times the capital X, capital Y, right? Because this is the standard basis, this is the other one, the new basis, which we want to represent the data in a better way, and then we move like this, right? So let's then multiply here 1 over square root of 2 times 1 minus 1, 1, 1 times capital X and capital Y. Would you agree here? Do you have any issue, Jung?
No, it's okay.
Okay, then this x, we can write this x as 1 over square root of 2 times 1. Capital X minus capital Y, okay? So I get it from this expression here. And similarly, we can obtain that y is equal to 1 over square root of 2 times capital X plus capital Y. Okay, so here we have two expressions, and then what we can do is let's substitute these values in the expression that was given initially. Okay, so if we do that, what do we get? So this is what we have, and then let's substitute them here. What is 5x squared? 5x squared, 1 over square root of 2 squared is 1 over 2 times x minus y squared. So this here we get x squared minus 2xy plus y squared. Then we have minus 6xy. If we multiply x and y, we get here 1 over square root of 2 times 1 over square root of 2, we get 1 over 2. So this is minus 6 times 1 over 2 times, what is a minus b times a plus b? It is a squared minus b squared, right? So this is x squared minus y squared plus 5y squared plus 5. What is y squared? It's 1 over 2 x squared plus 2 xy plus y squared. This is equal to 2. Okay? Then let's try to put together all of these numbers that we have on the board. So if we look at the term 2xy, we have here 5 over 2 times 2xy minus 2xy, we get minus 5. And then, if we look here, this is plus 5 over 2 times 2xy. So they simply cancel out, okay? So in here, this term cancels out this term. And then we look at this is 5 over 2 x squared plus 5 over 2 x squared. What is it? It is 5x squared minus 3x squared. We get 2 capital X squared, right? So these terms, we got done with those. And then we get 5 over 2y squared, which is this term here, plus 5 over 2y squared, this is 5, plus 3y squared, this is 8, plus 8y squared, this is equal to 2. Now, this is the new equation that we get. We see that, and this equation, if we try to use the same, a similar representation like in here, how would we do it? The way to do that, it could be the following. We can have capital X, capital Y, which is the X transpose. We multiply this one with 2, 0, 0, 8, multiplied by capital X, capital Y. This is all equal to 2. Okay? Now, what we see here is that the matrix representation, here we have the matrix which is 5 minus 3 minus 3, 5, and here this matrix representation, it is kind of updated or it's changed slightly. So in the standard basis, we could write this one 5 minus 3, 5 minus 3 minus 3, 5. Okay. What this represents a linear transformation. Okay, and it looks like this matrix in the new basis, what it becomes, it is 2, 0, 0, 8. 2, 0, 0, 8. So we have a 2 by 2 matrix. This is how this looks in the new domain. Now, do we have any question for so far? Okay, so this is what we obtained here, and then what we can do here, we can ask a different question. The question that we can ask here is, and you will understand why we're going to do this. The question is the following. If we have this matrix, which in the standard basis, it looks like 5 minus 3 minus 3, 5. So here we have, this is the matrix A. So this matrix A, if we multiply this with any vector x, okay, for which values of x, this matrix A is not going to rotate the vector. So we are coming up to the first question we asked in today's class. So we said that, is it possible to find for a given matrix A, which in this case, in our example, this matrix A is this one, which is 5, 3, minus 3, 3, where in the standard basis. And the question is this now, given, so this question, it is the same as your previous homework, where you were given a matrix A, and you had to find a pair of vectors A, AP, or not. So given this, find a vector X such that no rotation. So let me write it like this, such that you get no rotation. So in your homework, you were considering, wait a second, so this is here. So how can you, yes?
Could you say that if you multiply that equation by the inverse of matrix A,
yes,
you have found, like, then you have found one which does not make any rotation, just it scales.
So you are saying this, right? You are saying that if we multiply A inverse with A with X, this would be lambda A inverse times X, right?
Yes, so you would have just the identity matrix on the left.
This is perfect. Your intrusion is very welcome because you observe here that x is equal to lambda times A inverse times x. Now, if we want, yeah, this is, let me think for a moment. And then this system of equation, this can also be written like this. 1 over lambda times x, this is equal to A inverse times x. So 1 over lambda times x, this is equal to a matrix B times x. Right? So what you are suggesting here, or what you helped us understand, is that it looks like for these specific values of x, we can find a matrix B, which if we multiply it with the x, this magnification will be inverse, okay? Because this lambda, it can be, let's assume that lambda is equal to 2. That means that you do A times x is equal to 2 times x, but then for another value, another matrix B, you do B times x is equal to x divided by 2. So again, what this matrix A can do, can magnify the given vector by 2. What the matrix B can do, it can divide in half the original vector x. Now, this property that you helped us to understand, this is a property of matrices which are inverses of each other. Okay? So, for any condition like this, the inverse, what the inverse matrix will do, will multiply the original vector by 1 over lambda. Okay? So, we can do it, but this can help us to understand the relationship between this and this. Okay?
Yes, if I'm not mistaken, when you multiply the vector by any scalar, you're only changing its magnitude, like it doesn't affect the angle, right?
Yes, that's correct, yes.
Okay.
But now, let's see here, how can you solve this system? So, what we can do is the following. We can do A minus lambda I times x, this is equal to 0. So, what is this equation? So what we need to do here, we need to solve for x. But have you ever seen this before? Have you ever seen an equation like this? And what did we call it before? So solving this system, it is equivalent to finding the null space of B. Okay? So where to find the null space of B? And what is one possible solution for this equation? B times x is equal to 0.
You have the trivial solution.
That's true.
But you can also have infinitely many, depending on how the equation is.
Yes, for any system of equation which is Bx is equal to 0, we have the trivial solution, but we don't want the trivial solution. So we get x different from 0 only if the determinant of B is equal to 0. And this, you know why this is the case, because we have solved systems of equations, and we know that if we do B times x is equal to 0, that means that the linear combination of the columns of B, they combine and they get a 0, but whenever x is different from 0, that means that the columns are linearly dependent. Okay? If the columns are linearly dependent within each other, then that means that if you linearly combine them, you can obtain one column which is full of zeros, which is equivalent to the case when we have a matrix where the rows are linearly combined, and we started the semester by calculating the reduced row echelon form, and if it happens that any one of the equations were any one of the rows was a linear combination of the other rows, what did we get when we try to identify the reduced row echelon form? We get a row full of zeros, right? If we get a row full of zeros, that means that we're talking about a case where the determinant is equal to 0. Okay? So Then let's see when is the determinant equal to 0. So what is the matrix we are dealing with? Let's not forget, we are dealing with this matrix 5 minus 3 minus 3, 5. So here we have the following: 5 minus 3 minus 3 and 5. We subtract here, we subtract minus lambda 0, 0 lambda. Okay, and this is equal to 5 minus lambda, minus 3, and 5 minus lambda. Okay, we want this determinant to be equal to 0. Now, these values, I think we understood this. This was the rotation of the matrix, so let's take this away for a moment. And then let's see. So here we have to find out, and this equation that we see. Wait a second. What is the determinant of this matrix? So this is the determinant, right? And this polynomial that we see here, this is called the characteristic polynomial. Characteristic polynomial. It is a polynomial of order 2, which means that the variable which we need to find, the lambda, it is to the second order. So this means that we are expecting two different values. If we expand this expression, what we get is that we have lambda squared minus 10 lambda minus plus 25 minus 9, this is 0. Then 25 minus 9 is plus 16, so this is lambda squared minus 10 lambda plus 16, this is equal to 0. Then, what are the solutions lambda 1, lambda 2 here? This is lambda minus 2 times lambda minus 8, this is equal to 0. So then this looks like lambda 1 is equal to 2, and lambda 2, is equal to 8. And Dirido, can you follow us here, Dirido?
Yes.
Okay, so we're trying to answer your initial question, which was, why do we do the change of basis? Okay, and now, Dirido, can you help us here? So if we find lambda equal to 2, for lambda 1 equal to 2, what values of x can we find? What we get, let's remember, the equation that we have to look for is this one. Okay, so here we have 5 minus 3, 5 minus 3, minus 3, 5, times a vector, which is AB, and this is equal to 2 times AB. How can we find the AB here? What is the first equation that we get from here, Irida?
5a minus 3b.
Yes.
Minus 3a plus 5b.
No, wait.
Equals to 2a.
Yeah, okay. Now, how many unknowns do we have here? Satanya
2.
We have 2. How many equations do you need?
2.
2. Do you have a second equation?
Yes, from the matrix.
What is it?
Minus
Say
3a plus 5b equals to b.
Is equal to 2b. What do we learn from the first equation? How can you simplify this? How can you simplify the first equation?
Move the a components at the same place and the b components on the other place.
So do you get something like this?
Yes.
What do you get from the second equation?
The same thing.
The same thing. So you have 2 unknowns, and you think you have 2 equations, but you really don't, okay? So you don't have 2 equations, you have only 1. Because they are linearly independent, because the determinant of this term is equal to 0, but that's fine. So can you find a pair of numbers A and B which can satisfy this condition?
Since A is equal to B, then I think there are infinite numbers, infinite pairs of numbers.
That's true. But let's pick up 1, 1. Okay? Let's pick up 1, 1. It is a possible choice. Then for the same way we do when lambda 2 is equal to 8. What is the equation? So when lambda 2 is equal to 8, we get 5 minus 3, 5. If we multiply this with AB, this is equal to 8AB. So what is the equation that you obtain in this case? Diridor, you go ahead, you continue.
5A minus 3B equals 8A.
This is equal to 8A. 8A. Do you have a second equation?
No.
No, you don't. Don't worry. Don't write it. It will be a waste of time. If you write it, you're going to get the same expression. So let's leave it with this. How can you simplify this a little further? What is this?
Minus 3B equals 3A.
Minus 3B is equal to 3A. So what is a pair of numbers which satisfy this condition? So this is a possible choice, right? So here we have 1, 1. When lambda is equal to 2, we get 1, 1. When lambda is equal to 8, we get minus 1, 1. Okay? Now, actually, I forgot a very important point here, which it is my mistake. But after we got this equation, can we draw this graph? That's 2x squared plus 8y squared. Diego, can you help me draw this graph? So let me take this out.
I think it's an ellipse.
The thing is an ellipse, that is correct. Where will this ellipse intersect the new coordinate system?
I'm sorry, what? Can you repeat?
So from capital X equal to 0, what we obtain from here is that 8y squared, this is equal to 2, and then y squared, this is going to be 1 over 4, right, from here. And this means that the y itself, this is going to be plus minus 1 over 2. Okay? And similarly, when y is equal to 0, I'm reading from this equation, we get that 2x squared, this is equal to 2, which means that x is equal to plus minus 1. So you are correct. This is going to be an ellipse, which when x is equal to 0, x is this variable. Okay? When this is 0, y is going to be half. It's going to be, wait a second, no, y is here. It's going to be here and here. This is 1 over 2. And when y is equal to 0, x is going to be 1. So here we have 1, and this is minus 1. So you get an ellipse, which is going to look like this. So it looks like we were given this equation initially. We wrote this equation using this matrix. This matrix is in a standard basis, it looks like this. Then we ended up with we changed the variables. We ended up with this equation, which was an ellipse, which was also easier for us to perceive. We noticed that the matrix that represents this new equation is 2008. This 2008, what they really are these values, which these are called the eigenvalues. Okay? These are the eigenvalues of this matrix. So this matrix A, which was in the standard basis, this is represented by linear transformation or a basis D in the new basis, which is a diagonal matrix. Working with diagonal matrices, it is an essential element of linear algebra. The major purpose of linear algebra is to teach to us how we can achieve diagonalization of a given transformation or of a given linear transformation. So here, did we diagonalize the matrix A? Yes, we did. Here we have it, right? And and this is why we see here this 5, 5. We have here some non-diagonal terms. And these non-diagonal terms, they describe to us the mixing of the terms or the coupling. You are going to be electronics engineers. In electrical engineering, you are going to learn that electric field, it is strongly coupled with a magnetic field. So you are the best students in this department that understand the best, practically speaking, how different quantities can be coupled. We do not like the coupling, okay? We want to decouple the variables because we want to represent the complete data set in a new reference frame where things are more clear, like in this case. If we try to draw the graph of this expression using the standard basis, which is described by 1, 0, 0, 1, or by the standard basis shown here in black, it might be a little difficult to pick it up or to understand how the graph is going to be. But if we change the coordinate system, this is relatively easier to pick it up, and it's also the best because we have diagonalized the matrix A. So in the previous session, we talked about that we are very good at figuring out how we can project, what's the name? How we can project one vector from one basis to another. Now, we want to see how we can represent this matrix A into the new basis. But the biggest question is this: how are we going to find this one? How? Because this is a new basis B, but we come to the question of Lirdor. Which one is the best basis? How are we going to find it? Now, the best basis, Lirdor, is composed of these two vectors that you identified together with me. So this new basis here, this is the basis 1, 1, 1, 1, and minus 1, 1, minus 1, 1. Okay? So the best basis, these vectors that we have found here, these are called the eigenvectors. These are called the eigenvectors. And these are called the vectors which, no, this is one is here, and the other one is here. So if we are given a matrix A, the eigenvectors correspond to the vectors that the matrix cannot rotate. Okay? So these vectors that are not rotated, these are very important because once we find those, we use them as a basis. If this is a basis, so let's assume that if this is a new basis, which it should be, then what we should obtain is the following. What did you say before? We said that the linear transformations, they are represented by, so matrix A, it was a linear transformation in standard basis, right? But the P inverse times A times P, this was in the new basis, B basis, right? We wrote this one in the previous hour, which means that if this is the matrix P, what is P inverse? P inverse, it will be equal to, we interchange these numbers, which will be the same, and we change the sign, this is minus 1, 1, this is it, okay? So then, let's multiply carefully what we get. What is P inverse? P inverse is 1, 1, minus 1, 1, times the matrix A, which is 5 minus 3, minus 3, 5, and then we multiply this with a P. What was P? It's 1, 1, minus 1, 1. So let's multiply these two initially. So this is equal to 5 minus 3, this is 2, minus 5 minus 3, minus 8. This is minus 3 plus 5.
Professor,
Yes.
at the P inverse, why don't we multiply with the 1 over determinant?
You are right. So what is the determinant here? Determinant is equal to 2, right? Or is it? Yes.
Yes.
Equal to 2. So here we get 1 over 2. And yeah. So we can multiply this 1 over 2. That's true. So let's continue here. So we get here, this is minus 3 plus 5 is 2. This is 3 plus 5, this is 8. And then we multiply it with this matrix. So let's write this one here, 1, 1, minus 1, 1. and this is going to be equal to 1, 1, this is equal to 4. Right? So then we have here 8 minus 8, this is 0. This is 0. Here we get 16. Divided by 1 over 2, what is this? This is equal to the matrix, which is 2, 0, 0, 8. So what we find here, we find that we have a diagonal matrix, D, which is diagonalized from A. How did we do it? Using the eigenvectors which were found over there. So this matrix D, which we diagonalize, we can also add the argument that we said that for any matrix D, which is related to the matrix A, like this, what are they? They are similar. So we said D is similar to A, but now D is much more than just being similar. It is a diagonalization of the A. So we see this everywhere. We see it here. We see the basics where we got it from. It helps us to understand this equation a little better. And yeah. So again, what we pick up from here, and also it can also be seen that this new basis, this is this point here. This is 1, 1, and this direction here is minus 1, 1. So the rotation of the original basis, or the standard basis, is done by this, and this would be our matrix P. Do you have any question? Okay, if you have no more questions, we'll still be available, but we're going to end this session.